So, in this lecture we will now start discussion on photodetectors. So, how do we detect an optical power? The idea is to convert optical energy into electric energy, and we think about it, the very first thing that comes to our minds is photoelectric effect. So, what is photoelectric effect? We know that if we have a metal and we incident optical energy onto it, we incident some photons, then these photons, if their energy is sufficient, then these photons can knock out the electrons out of the metal, and then these electrons are available for conduction. These electrons are collected on an electrode, and this can constitute a current in a circuit. So, we can convert optical energy into electric energy using photoelectric effect. Photoelectric effect occurs in metals where you have free electrons in conduction band, and these electrons, although we call them free electrons, but they are still attached to the material with certain energy which is known as the work function, and this work function is W. Now, if the energy of the incident photon is large enough which can overcome this work function, then this photon can knock out this electron and it can make it absolutely free. Then it is not any longer attached to the material. The rest of the energy appears as the kinetic energy of the electron, and by the equation of conservation of energy we can have H nu is equal to W plus E max. E max is the maximum kinetic energy of an electron which occurs for the most loosely bound electron. But if we do the same thing on a semiconductor, then what happens? In a semiconductor we have a valence band and conduction band, and these bands do not overlap. We have a band gap between them, and most of the electrons are in the valence band. So, now if you want to knock out an electron from a semiconductor, then you will have to incident a photon of energy which can overcome this band gap, so that the electron can go into conduction band, and then you have the work function chi. So, it has to overcome this work function also, then it can come out of the material. So, the equation of conservation of energy now is transformed to H nu is equal to E g plus chi plus E max. E max is again the maximum kinetic energy of the electron. So, you would require, you can see you would require much more energy to knock out the electron from a semiconductor as compared to what you need in the case of metals. So, what do we do? Do we really use this effect, which seems to be quite inefficient, because you would require very high energy of the photon, and this will have a consequence on the wavelength that you can detect? Well, in semiconductors, when we use semiconductors for photo detection purpose, then we usually do not require to knock out the electron, but we use what is known as internal photo effect. What is internal photo effect? Well, we incident a photon onto the semiconductor material, and depending upon the energy of the photon, depending upon how the energy of the photon compares with the band gap energy, this photon can be absorbed or this photon can go as it is. or see this semiconductor material as a transparent material. So, if h nu is smaller than E g, then this photon will go as it is, it will not be absorbed. However, if this h nu is larger than E g, then this photon will result in the generation of electron hole pair. The electron in the valence band will get this energy and will go to the conduction band. So, the absorption of photon will result in generation of electron hole pair, but these photoexcited carriers, they remain within the sample, within the material, they do not leave it. And then if we apply an electric field, then this would result in the transport of electron and hole and consequent flow of electric current in electric circuit. The devices which are based on this effect are PN junction semiconductor photodiodes, PIN photodetector and Avalanche photodetector APD. So, we will study all the three in this lecture. If I look at PN junction photodiode, how does it work? If I just take a simple PN junction diode, then I know that in the junction region there is an internal electric field which points from N type to P type, because on N type you have positive ions and on P side you have negative ions. And if I look at IV curve of this PN junction diode, then it is something like this. If you do not apply any bias here, then you are somewhere here, no applied voltage, no current. When you forward bias it, then you get a forward bias current like this, and when you apply reverse bias, then you will have reverse saturation current like this, very small amount of reverse saturation current. Now, what you do, you incident photons on this, you incident optical energy onto this PN junction diode. Now, if the energy of these photons is sufficient to generate electron hole pairs, it is larger than the band gap, then this will result in generation of electron hole pairs everywhere. Now, I have divided this into three regions, 1, 2 and 3 on either side, and see what happens. Still I have not applied any bias onto this. Please see, this plus minus do not indicate any bias. I will explain what it is. Now, let us look at an electron hole pair which is generated in this region. Since you have an electric field which points from N to P, then this electron will be drifted towards N type and hole will be drifted towards P type. Any electron hole pair which is generated in this region, then electron will move to this side and hole will move to this side. The electron hole pairs which are generated in these regions, they will wander randomly unless they come in the vicinity of this electric field, and when they come in the vicinity of electric field, then they will be drifted, electron on this side and hole on this side, similarly this one. While the electron hole pairs which are generated here, they will wander randomly and they have very less chances to come in the under the influence of this electric field, because they are very far from here, and then ultimately they will recombine. So, what do I see? That electron hole pairs which are in this region or which are in these regions, they have the probability of constituting an electric current if the circuit is closed. But if the circuit is not closed, then what happens, that electrons gather on this side and holes gather on this side. So, basically what I have done, by incidence of optical energy, I have generated electron hole pairs, and because of this internal electric field, there is charge separation. Electrons on n side, holes on p side, and when there is charge separation, then it works like a battery. Depending upon how much charge has been created, I will have an open circuit voltage. So, it will become a battery. You have a p-n junction semiconductor diode, you incident optical power on it and it becomes a battery. This is nothing but the solar cell. So, if I look at IV curve, then the IV curve in the presence of photon flux, phi represents the photon flux, becomes like this. And since I have not applied any voltage here, bias voltage, so V is 0. Okay. So, I have not applied any bias voltage, but because of the charge separation, a voltage occurs, a voltage appears across the terminals, which is VOC, and it is known as open circuit voltage. This is open circuit voltage. Now, what happens if I short circuit it? If I close the circuit, then electrons will start flowing in this direction, hole will start flowing in this direction, and it will constitute a current. But this current would be larger than the reverse saturation current in the absence of any optical energy. So, the optical energy increases the reverse saturation current, and this reverse saturation current is a measure of whatever optical power is incident, and that is how we can measure optical energy or optical power. This is nothing but the short circuit operation of an unbiased p-n junction diode. You can also bias it. If you bias it and you reverse bias it, when you reverse bias it, then what you do, you basically increase the width of this region, depletion region, and you have this region, wider depletion region, which has electric field across it. And since this region is now wide, so you will have more electron hole pairs here generated, which contribute towards photocurrent. So, this reverse biased operation of a photodiode results in a photodetector or photodetection process. So, you operate somewhere here. So, these photodiodes are usually operated in strong reverse biased configuration. What are the advantages of reverse biasing it strongly? Well, a strong reverse bias will create strong electric field across the junction, and since the electric field is strong, so it will increase the drift velocity of the carriers, and consequently it will reduce the transit time. Also, as we had seen, the reverse bias will also increase the width of the depletion region, and because of that the photosensitive area would increase. So, depletion region layer width will increase. So, photosensitive area would increase because it is that region where the generated electron hole pairs will constitute a current. Another thing is that when you increase the width of the depletion region by strong reverse bias, then the junction capacitance decreases, and this decrease in junction capacitance will improve the response time or the bandwidth. So, these are the advantages of strongly reverse biasing a p-n junction diode for photo detection process. Another important photodiode is PIN or pin photodiode. What has been done here is that you insert an intrinsic region or lightly doped region between p type and n type. What is the advantage of this? Well, with this you extend the width of the region which supports the electric field, and thereby you increase the area of photosensitive region. So, if I look at it, then this is the electron energy as a function of distance. So, you have p type, you have n type, and this is the junction region where you have an electric field. If I look at the fixed charge densities, which are negative ions on the p side and positive ions on the n side. So, this is the fixed charge density which creates an electric field like this, and since this region is very wide, so the electric field is now over a very wide width, very wide region, and it increases the photosensitive area. So, what are the advantages or consequences of inserting an I region? Well, as I had explained in the previous slide, that the area available for capturing light increases, because now this area becomes photosensitive. This is the drift region because the electric field is over this region, and then this is the diffusion region where the electron hole pairs wander randomly and then they come under the influence of the field here and get drifted later on. So, the area available for capturing light increases. Again, the junction capacitance will decrease because now the width of the junction region increases considerably. So, the junction capacitance will decrease because junction capacitance goes as epsilon A over W, where A is the area of cross section and epsilon is the dielectric permittivity of the medium here. So, the RC time constant also reduces. However, you will say that you have increased the width of this region. So, now electrons will have to travel longer distance in drifting from here to here. So, it will increase the transit time as compared to the transit time in the case of simple p-n junction diode. Yes, it will increase the transit time, but increase in transit time has very less effect on bandwidth as compared to this RC time constant. So, it is not of major concern. Also, what I see that now drift region is much longer as compared to diffusion region, and of course, drift process is much faster than the diffusion process. So, you will have faster response of the photodiode, PIN diode. There is another device which is known as Avalanche photodetector or Avalanche photodiode, APD. This device is a very sensitive device because it has an internal gain mechanism. and it operates under very strong reverse bias. What it is? Let us look at the structure. The structure is, you have a highly doped p region, then you have a pi region which is nothing but lightly doped p region, then you have a p doped region and highly doped n region. If I look at the fixed charge density across various layers, then you have very high negative charge density here in the p plus region, and the lightly doped p region will give you moderate fixed charge density. Then this is the charge density of p region, and this is in n plus 1 region positive charge density. This kind of charge distribution will result in the electric field which looks like this. So, I have electric field which extends over a very wide region, and then very strong electric field here. Now, if I operate it under very strong reverse bias, then in this region you have very strong electric field, and this strong electric field will accelerate the charges rapidly. What is happening? Basically, you incident photon, it will generate electron hole pairs. So, these electrons, when they come under the influence of such a large electric field, they are accelerated, and since they have very high energy, so these electrons now have impact with the electrons in valence band, and they give a part of the energy to an electron in valence band, and then this electron goes to conduction band. So, another electron hole pair is generated. This electron from the newly generated electron hole pair again is accelerated and knocks out another electron from, sends another electron from valence band to the conduction band. So, another electron hole pair is generated. So, there is avalanche multiplication of carriers, and this gives the internal gain. But to have this avalanche multiplication, what you need is very strong reverse bias. So, you need hundreds of volts of reverse bias for this. What wavelengths would be detected by a particular material of a photodiode? For that, if I look back to this EK diagram, what happens is that only the photons which have energy larger than the band gap energy can create electron hole pairs. So, it will have a cutoff. If the photons have smaller energy than Eg, then they will go through, they will not be absorbed and they will not contribute for photocurrent. So, there is a cutoff wavelength which is given by lambda c is equal to 1.24 over Eg, where Eg is in electron volts and lambda c in micrometer. This we had seen earlier also. So, for all the wavelengths longer than lambda c, they cannot be detected by the photodetector because their energy would be smaller than band gap energy, while all the wavelengths which are shorter than lambda c, they will have energy larger than Eg and they will lead to generation of electron hole pair and photocurrent. What are the various characteristics of photodetector? Well, one is quantum efficiency, how efficiently I can convert optical energy into electric energy. So, it is a measure of electric power generated per unit incident optical power. So, you have the semiconductor material you incident photon and you generate photocurrent. Well, so the quantum efficiency is defined as number of generated electron hole pairs that contribute to photocurrent divided by number of photons incident, because each photon will generate one electron hole pair, but not all the electron hole pairs will contribute to photocurrent. Some of them are lost in recombination. So, there is a finite quantum efficiency. Let us work out the expression for it. If I have a semiconductor material which has absorption coefficient alpha at wavelength lambda and it has got width w. If I incident optical power P naught here and if I do not take into account any Fresnel reflection, then the transmitted power would be P 0 e to the power minus alpha w, if alpha is the absorption coefficient, right. So, what is the power which is absorbed? The power absorbed would be P 0 minus P 0 e to the power minus alpha w, which means P 0 times 1 minus e to the power minus alpha w. Now, basically P 0 is not the power which enters the material, because a fraction r will get reflected because of Fresnel reflection. So, the power that goes inside is 1 minus r times P 0. So, this would be the power absorbed and this will result in generation of electron hole pair. Okay. So, the number of photons absorbed would be now this divided by h nu, number of photons absorbed per unit time, and each of these photons will generate electron hole pairs, and if only zeta fraction of generated carriers contribute to photocurrent, then the number of carriers that contribute to photocurrent would be zeta times this. Again, this is per second. Now, what is the total number of photons incident? Total optical power incident divided by energy of one photon. So, these are the total number of photons incident per unit time. So, the quantum efficiency would be this divided by this. So, eta would be this and this is simply zeta times 1 minus r times 1 minus e to the power minus alpha w. What would be the photocurrent? Well, the number of carriers that contribute to photocurrent per unit time times the charge of one photo generated carrier. So, this would be given by this. You should note that each generated EH pair contribute to charge E. So, this would be the photocurrent. Okay. Then another important parameter is responsivity. Responsivity is output versus input of a device. Output here is photocurrent and input is incident optical power. So, R would be IP over P 0. So, simply it would be this, and since this is eta, so it can be represented in terms of quantum efficiency as eta E over h nu. In case of APD, you will have a multiplication factor because of internal gain. So, this will become m times eta E over h nu. These are the quantum efficiency and responsivity at various wavelengths. As I can see that not one material can work in the entire wavelength range. So, you have different materials to work in different wavelength ranges and they have different quantum efficiencies also. For example, silicon can work from 400 nanometer to 1100 nanometer, germanium from 800 nanometer to 1800 nanometer, and indium gallium arsenide from 900 to 1700 nanometers. This is the responsivity of silicon. This corresponds to eta is equal to 1, which is ideal photodiode, and this is typical silicon photodiode. Then the speed of response, speed of response and hence the bandwidth, it depends on transit time, how fast the carriers transit across the junction. And transit time is nothing but the width of the junction region divided by the drift velocity. For silicon pin detector, W is typically 20 micron, drift velocity of electron is 10 to the power 5 meters per second. So, the transit time would be 200 picoseconds. In case of indium gallium arsenide pin detector, W is 5 micron. So, transit time would be 50 picoseconds. And the electrical frequency response is determined by RC time constant, because if you incident this optical pulse, then the electric pulse will follow this, because there would be finite rise time and finite fall time, which depends on RC. And this bandwidth, because of this, the bandwidth would be limited by RC time constant and is given by 1 over 2 pi RL CD. RL is the load resistor, CD is the junction capacitance. Junction capacitance is given by epsilon A over W. So, of course, smaller the junction capacitance, larger would be the bandwidth. So, in the end, let me work out an example. So, if I have silicon pin photodetector with diameter 500 micron, junction width 20 micron and epsilon this much, in CD would be 4 picofarad. If I have a load resistor of 1 kilo ohm, then bandwidth would be about 40 megahertz. In case of indium gallium arsenide pin detector, CD would be around 0.5 to 2 picofarad, typical rise time is 0.06 to 0.5 nanoseconds, and it will give you the bandwidth of about 0.3 to 2.5 gigahertz. So, with this I complete discussion on optical sources and detectors, and in the next lecture I will now consider the system design aspects. Thank you.